Hello, my name is Kevin Shabahang and I'm going to present some models of free associations. This is a pre-recorded presentation for the 2021 Australasian Mathematical Psychology Conference. I did this work with the help of Professors Hyung-Woo Kim and Simon Dennis. In the free association task, you are given a cue and are asked to report the word that immediately comes to mind. Over many trials and participants, stable patterns of association emerge between concepts. Many workers suggest using patterns of human free association as a way to ground formal theory. First, I'll briefly review some influential models of semantic processing and how they can be used to model free associations. Then I'm going to present our own dynamic systems view that treats free associations as steady states in a system whose state space is altered by the cue. We consider two classes of modeling: high-level descriptive accounts and low-level process models. Griffith and colleagues already modeled free associations using latent semantic analysis and the topics model, two descriptive accounts. Here we replicate their findings and extend the work by considering another high-level account by Mikolov and colleagues called word-to-vec. Finally, we consider two process accounts, BEAGLE by Jones and Mewhort and the Dynamic Eigen Net, which is an associative net I helped develop with Professors Hyung-Woo Kim and Simon Dennis. Early work focused on word-by-document co-occurrence statistics. Over a set of documents, the number of times each word occurs in each document is tallied in a matrix. Each word can be represented as a point in high-dimensional space. Landauer and Dumais suggested using singular value decomposition to factor the word-by-document matrix into two orthogonal matrices and a diagonal matrix. They suggested approximating the original space and squeezing it into lower dimensions by discarding a subset of the components. The compression enhances relationships between words that occur in similar contexts. For example, given you studied the following two sentences, each in a different context or document, notice that the word feathers occurs in both contexts. Dimensionality reduction merges the context boundaries by pulling words that occur with the same words closer to one another. Although eagle and falcon didn't occur together in the same context, they are pulled towards each other through feathers. An alternative approach is to assume that each document is made up of a set of latent topics. We can treat each document as a probability distribution over those topics. We assume that a document is generated by first sampling a topic from its topic distribution, then a word is sampled from another distribution conditioned on the sampled topic. Instead of considering the decomposition in terms of spatial dimensions, the topics model decomposes the word-by-document matrix into a matrix of conditional probabilities of words given the topics and another matrix of conditional probabilities of topics given the documents. Griffith and colleagues use a Dirichlet prior on the two conditional distributions and use Gibbs sampling to estimate them. Mikolov and colleagues offer a feed-forward neural network approach. In their continuous bag of words variant of word-to-vec, they use a sliding window over text and treat the word in the center as a to-be-predicted target using its surrounding words. The surrounding words are fed as input and project to a hidden layer of lower dimensionality. The hidden layer projects to an output layer that gives a probability distribution over possible target words, given the context. The network is trained to maximize the conditional probability of the target given the context. In addition, a set of irrelevant words are sampled for each context-target pair, and the network is also trained to minimize their conditional probability given the same context. Training is done using stochastic gradient descent with simulated annealing. Both LSA and topics are high-level accounts. They do not specify an incremental learning algorithm. Word-to-vec has face validity as a process model, but it requires many passes through the training data to learn. This is also true of the topics model when using Gibbs sampling. Jones and Mewhort present the BEAGLE algorithm, which learns continuously and only requires a single pass through the data. Whenever a novel word is encountered, BEAGLE assigns it a Gaussian vector by randomly sampling each element from a zero mean normal distribution with variance 1 over n. N is the dimensionality of the vector. The placeholder vector for the words remain fixed after the first time they are generated. Another set of vectors called item vectors encode each word's history of usage with other words with which they co-occur. As with Word2Vec, BEAGLE assumes a fixed size sliding window over the text. At each slice, the item vector for each word in the window is updated by accumulating the placeholder vectors for the other words into its item vector. Over time, the item vectors stabilize to patterns that capture the history of usage of the corresponding words in the training corpus. In all the models we've described, some form of abstraction occurs on the original word by context representations. In LSA, it's through linear dimensionality reduction, whereas in Word2Vec, it is through nonlinear dimensionality reduction. The topics model implements abstraction through latent variable estimation, and BEAGLE vectors use Gaussian vector accumulation. We suggest an alternative approach where abstraction occurs during retrieval in a dynamical system. Take the two contexts we introduced earlier. We can represent the connections between words that occur in the same context together in an associative net. Our network's memory is a word-by-word matrix of weights derived from co-occurrence counts between words in a sliding window. The network is also characterized by a momentary state vector. We can probe the system by initializing its state to have a Q word active, such as eagle. We run a single iteration by multiplying the state with the matrix and unit normalizing the outcome. This spreads the activation from the original Q word to the words with which it's connected by one hop, that is, the syntagmatic associates. Now we can take the output from the first iteration and use it again as input to iterate a second time. Because feathers became activated after the first iteration, this time it activates its neighbors, such as falcon. In practice, we run the iterations many times until the system settles to a steady state or an equilibrium. We believe that in this way, latent relationships between words emerge online and at retrieval. See Kelly and colleagues for an interesting discussion of higher order associations. The weight matrix in our case is square and symmetric, which means it can be decomposed into a set of eigenvectors, denoted by the capital E, and a set of eigenvalues, denoted by capital lambda. The original matrix is the sum of the outer products of each eigenvector, weighted by its corresponding eigenvalue. Suppose x0 is the state vector initialized with a given q. A single iteration is shown on the right-hand side of the following equation in terms of the eigenvectors. It says that the output is the sum of the eigenvectors of the original matrix, each weighted by the corresponding eigenvalue, and the dot product between the input and the eigenvector. After t iterations, the eigenvalues in the equation are raised to the tth power. But note that the eigenvalues fall in magnitude from the first eigenvalue to the last. This implies that in the limit, the output of the system will always correspond to the dominant eigenvector. This limits the associative net as a memory system. Models like the brain state in a box and the hop field net enable other steady states by introducing nonlinearities. We propose an alternative solution which preserves the system's linearity. In what we're calling the Dynamic Eigen Net, the outer product of the initial state is added to the weight matrix before recurrence and is removed after the system settles. The right-hand side shows how adding the outer product introduces a new term. We can use parentheses to emphasize the scalar terms in the equation. In a dynamic eigennet, we not only have the eigenvector term as we did in the linear system, but we have an additional term corresponding to the initial state. Namely, the initial state is added to the output, weighted by its dot product with the momentary state. The additional term acts as an anchor to prevent the state from moving too far into the distance. It changes the original space. We introduce two new terms, E prime and lambda prime, and suppose they correspond to the dominant eigenvector and value of the modified weight matrix. Then in the limit, the system converges to the sum of the eigenvectors, each weighted by its eigenvalue and dot product with the momentary state, plus the initial state weighted by its dot product with the momentary state. The right-hand side shows this term corresponds to the dominant eigenvector of the altered matrix. In our simulations, we add a weight to the outer product term to ensure it is higher in magnitude relative to the dominant eigenvalue. We set the weight to be the dominant eigenvalue plus some small number. To encode, we use a matrix that records the co-occurrence of word pairs. The counts are derived by sliding a window through the corpus. Using the raw co-occurrence counts yields a sharp drop in eigenvalues. One of the requirements for the dynamic eigennet to work is that the eigenvalues should be relatively uniform. In the least, they cannot drop too sharply from the largest to the smallest eigenvalue. We let the function r of v with respect to u be the rank of word v in word u's neighbor co-occurrence counts. So if word v was the most frequent word to co-occur with word u, it yields a rank of 1. We set the weight of the dynamic eigennet to be the log of the co-occurrence counts only if both words are in the top d rank with respect to one another. We use the max degree d of 64 for the following simulations. The max degree rule flattens the eigenspectrum, but not entirely. In LSA, word2vec, and BEAGLE, the vector cosine is used as a measure of similarity between words. The cosine of each q word's vector is evaluated with all other words, and the words are ranked in decreasing order of their similarity. We can match the models with the free association data by checking how far down the similarities the most common response for a given q falls. The same approach is used in the topics model, but instead of cosines, the conditional probability of each response given the q is calculated. Griffith and colleagues reported a median rank for the first associate of 31 out of 4,470 words for LSA and 18 for the topics model. The number of times the first associate ranked 1 was 11.54% for LSA and 16.15% for the topics model. We matched their corpus as best we could and used the 5 models we have discussed to predict the free associations. For each model, we show the percent of times the most common human free associate ranked the highest, followed by the median rank of the most common associate. We get similar scores for LSA and the topics model is what was reported by Griffith and colleagues, suggesting our corpora are well matched. In terms of the first associates, word2vec outperforms topics and the rest of the models, while Dynamic Eigen Net outperforms BEAGLE and LSA. In terms of the median ranks, word2vec outperforms all the other models. LSA performs better than the Dynamic Eigen Net, but the Dynamic Eigen Net still outperforms BEAGLE. We can correlate the ranks across the queues between the models to get an idea of their similarity. In this case, word2vec is the most similar to LSA. Topics, on the other hand, is most similar to BEAGLE. Recall the 2 sentences we mentioned earlier. We say that words which occur in the same context have a syntagmatic association. Words that precede or follow the same words, but not necessarily in the same context, are said to have a paradigmatic association. We can also characterize associations based on serial order, whether a word follows another or precedes it. Finally, we can consider overlap in either the phonological or orthographic forms of word pairs. We had 5 raters categorize word pairs into one of 5 association types. Then we took one of the word pairs and used it as a cue and checked the rank of its associate. We can group the word pairs into bins based on the dominant association to characterize the models. Unsurprisingly, the form-based category yields the highest median ranks. Surprisingly, all 5 models favor paradigmatic associations, followed by syntagmatic in serial order. The descriptive accounts outperform the process models. In LSA and topics, it may be that the word by document input provides more constraint than a sliding window. In word2vec, it's likely that the negative sampling optimization is what leads to good performance. Dynamic Eigen Net performs slightly better than BEAGLE. Because Dynamic Eigen Net's abstract at encoding, they are more suitable for context-dependent processing. Overall, about 80% of the first associates were not predicted by the best model. One possibility is that the language environment of the participants was not captured by our corpus. Another possibility is that extra-linguistic information is necessary, such as visual or affective information. In conclusion, dynamic eigennets provide a good process model of the task, but we still have a long way to go. Thank you.